So this work is part of a bigger project called MeTLS on building a verified open source TLS implementation of TLS 1.3, but also older versions. And and MeTLS itself is part of an even bigger project depicted here. Ask you in the end what this is. So while downgrade is just a small piece of the puzzle, it's a very important piece because a small downgrade slip can make you lose a lot of security, potentially all the security. So I want to introduce a downgrade on a everyday experience. So you get downgraded when an attacker can make you fall back on weaker security solutions when stronger ones are available. And I claim that we are very used to doing that. So downgrades can happen at the user level and the application level, but also at the protocol level. And this is the topic of my talk. So by now you've heard about TLS 1.3 and why it is important. So for the purpose of my talk, I want to emphasize that TLS is not a single protocol. It's a suite of protocols that have a negotiation mechanism that is widely used to negotiate multiple versions and many more cipher suits. This happens in the hello message of TLS, in which the client first sends all the stuff that he supports. The server chooses and sends back his own and sends back his decision on what to use in his hello message. TLS also supports a rudimentary downgrade protection mechanism as part of the key confirmation techniques that were discussed, I think, in the second talk, or in the first talk. So the configurability of TLS allows it to adopt new cryptographic algorithms while still supporting backward compatibility. So you've seen a similar slide before, but this is split up into different types of attacks. And this that allows a quick or agile reaction to new cryptographic weaknesses. So you can turn off old crypto and turn on new crypto. So particularly, people think that this is important to be prepared for quantum computers and quantum attacks. However, it also enables downgrade attacks in which an attacker can exploit this negotiation to make client and servers use weak cryptography. And the highlighted attacks here use some form of negotiation and downgrade. So we believe that the increased number of attacks is due to increased scrutiny after the Snowden leaks, but also the renewed interest in TLS because of the new version, TLS 1.3, and the two are linked. So in our opinion, it's high time to get things right, but the fact that most of these attacks are outside existing security models, and just some of the previous works were trying to kind of to capture some of those attacks, it shows that we are still somehow in a wild west of TLS attacks, where typical cryptographic security proofs do not tell us much about real-world attacks. So I will single out 3 attacks, kind of it's my Western heroes, and I will call them the good, the bad, and the ugly, and I will use them to illustrate the challenges of obtaining downgrade security. So summarizing our main contributions. So we have 2 general contributions for making kind of the wild west of real-world protocols a bit more orderly. One are downgrade definitions, and the other is a modular proof strategy for proving downgrade. So in addition, we have protocol-specific contributions in terms of attacks and also security proofs in our new model. So our goal here was to really stretch our first 2 contributions to see how they can deal with different protocols being thrown at them. So I will focus throughout on TLS, and in particular on TLS 1.3 for our positive results. So the 2 main contributions that I will talk about in this talk are the downgrade secure definitions that capture downgrade aspects of the previous attacks, That's the first contribution. And the second contribution is a modular proof of the downgrade fixes to TLS 1.3 that have been developed together with the core design team of TLS 1.3 and that are included in the new, I think, draft 13 of the standard. So setting the stage for the definition, I kind of want to give some notation for negotiation. So negotiation starts from client and server configurations that describe what versions and algorithms, cipher suites and modes client and servers are in principle willing to support. Then there's a multi-round negotiation in which parties send messages to each other, and the outcome of that is a mode, which contains the negotiated version and cipher suite. So we modeled the ideal outcome of negotiation using a preference function nego that maps two configurations to the mode that parties would like to get. Typically, this is what they would get if there is no active attacker present. So let me explain using that terminology why existing security definitions do not capture downgrade. So I take authentication as an example. And typically, authentication says that if my negotiated mode uses strong algorithms, then my partner and I agree on the keys, the identities, the mode, and potentially the whole transcript. But even that is not secure to guarantee downgrade protection, because authentication does not guarantee negotiation of a strong mode. That's basically where it starts off of. So if one only has such security guarantees available, what is required is the intersection of all modes must be strong. Intersection of the client and the server configuration should only support strong modes. But what if the client and server configurations support legacy algorithms for backward compatibility? And what are the minimum requirements on the configurations to achieve downgrade? So these three bullets match up nicely with the three attacks that I will refer to in my talk. So let's assume for a moment that we have an accident TLS handshake that uses strong algorithms as proven secure by cryptographers. For example, take those of the previous talks. So the first motivating attack, Boodle, exploits weaknesses in the record algorithm of old TLS versions. And its negotiation is prevented by modern handshake that authenticate the negotiation using the finished messages. So as the whole handshake is assumed to be secure, it falls within the scope of traditional provable security results. And indeed, the closest prior work by Dowling and Stabler showed this. So this is somehow the good case. This is what we could do before our paper. But what about the following attack that is reminiscent of logjam? So the server proposes, so the client proposes his preferred group, a strong group, but also a weak group. The active manual attacker makes the server fall back to the weak group. And now they do a standard signed Diffie-Hellman in which the server signs the key shares. At this point, the parties can compute the keys, and I mean actually all parties, because by breaking this good logarithm for the smaller group, the man in the middle attacker can also compute the key K, and then forge the finished message. So this is a break of key confirmation and breaks downgrade security of TLS 1.2. So there's some hope of achieving a stronger property, namely one could sign the whole transcript here as in TLS 1.3. But this is not captured by existing models, which assume that the whole handshake has a strong mode. So this kind of, the security against logjam-like attacks cannot be modeled in existing security proofs. What we would like instead is a stronger attacker model in which almost all of the handshake can be broken, and we rely on security only of a few downgrade critical algorithms, paradigmatically the signature scheme. And I think that was what one of the speakers referred to when they said that they want to look into stronger attacker models in the tamarind setting. So we are talking. So we still need some good cryptography. So that's kind of the ugly attack. So if you have a downgrade attack on the actual signature scheme, for instance, a very old hash function, and this attack was published at NDSS just beginning of this year, then there's really no way we can help you as protocol designers. So these attacks should be really carefully watched, and old hash functions and signature schemes should be eliminated. So there I support some Wild West style. So more formally, to capture this stronger attacker model, we formally define a downgrade predicate, DP, that holds when a client and server configuration jointly provides downgrade security to the first party. So here the client. So you can swap things around to define downgrade security for the server. For TLS, I think I give this primarily as an example, the details can vary. The predicate requires that the client demands good public keys and signature algorithms, and that the server expresses a preference for a downgrade secure version in its protocol. So we'll get back to this requirement when we analyze TLS 1.3. The goal of the negotiation is backward compatibility, so clients and servers can still interoperate with everyone. So in particular, the client can interact with servers that support only old versions. And the server can interact even with clients that do not support a strong signature scheme. And moreover, both clients and servers can support weak groups. So this is a quick primer into key exchange models adapted to this more general attacker model. So we have a man in the middle that creates long-term keys and protocol instances. And when initializing protocol instances, he provides them with their configuration. So the attacker can adaptively choose what these parties are willing to negotiate. Then he drives the protocol by using a send oracle in which he provides messages and receives messages, acting as a man in the middle. And as the sessions progress in the execution of the protocol, they assign variables which will be used to model security. So there are the configurations, there are some unique identifiers, typically a concatenation of nonces of two sessions, and the mode that is negotiated. And there can be more such variables for other protocols. I think in the key confirmation talk, there was also a very similar way of formulating security properties. So the goal of the attacker is to make instances reach a bad state where the attacker wins, so a winning state. I will indicate those states in red. So using that framework, here's our definition of downgrade security. So the winning state for the attacker, and this is the probability that we want to bound, is when there are two instances that have the same unique identifier, but, and for which the downgrade predicate on their configuration holds, but the instances, or the first instance, the client instance here, assigns a mode that is not the outcome of the ideal negotiation. So that would constitute a downgrade break. And an attacker that can get into this state with non-negligible probability, or with high probability, is a successful downgrade attacker. So there's a caveat to this definition, namely, what if the attacker can impersonate the server? So there's no server instance that has the same unique identifier. In that case, our definition says nothing and doesn't guarantee anything good about the mode. So in our paper, however, we show that we give a separate security definition, partnering security, for which exactly this is the winning state of the attacker. And we show that for typical key exchange protocols, whenever they are, that are downgrade secure, have also meet this partnering security property. So this is all I can say here about downgrade definitions. So please refer to our paper. In particular, there we give much more details on how the downgrade security relates to standard security properties, such as authentication and key secrecy. So when discussing our modular proof strategy, I will again focus on TLS 1.3. Please have a look at our paper for results on many other real-world protocols. So as everyone working on TLS knows, the standard is very complex. And usually the first step when writing a paper or doing some analysis of TLS is to simplify the protocol. So our second contribution is to show how this can be done in a sound manner. So we don't claim much novelty here, but we hope that these techniques will be picked up more, because it's really kind of this soundness issue of looking at partial protocols that miss attacks is really a big problem. And there's a very nice work also that exposes a nice exposition of this by Wogaway and Steger already in 2008. So there's really no excuse for not showing these simulations. So how does this work? So there's the complex protocol, which you get from the standard. And then you extract from that protocol a sub-protocol that can be extended to the complex protocol using a simulator. And the simulator helps to translate every attack on the complex protocol, on the full protocol, into an attack on the sub-protocol. So if you manage to prove the sub-protocol secure, then you also prove the full protocol secure. And we did that for TLS 1.3. So here is the downgrade sub-protocol. It starts off by the client sending its negotiation proposal. The server can reject proposals if it doesn't support any of the groups in that proposal, and then the client sends a new proposal. After that, the server chooses its mode and signs the whole transcript until then to the client. So the downgrade security should come from the signature on all of those messages. However, TLS 1.3 missed the retries. So the session hash started after the retries. This is one of the fixes that we proposed. And there's another fix that does something fancy to the server nonce, which I will get back to in a bit. So the good news is that for this patched downgrade protocol, we can show, we can prove security. And the proof relies on the uniqueness of nonces and the security of the signature scheme, as well as the server signing all the network input to the nego function and the result. But what about version downgrade? So we can show that downgraded TLS 1.3. So can we downgrade TLS 1.3 to TLS 1.2 and remount logjam? So unfortunately, there's nothing in the TLS 1.3 standard that could prevent such downgrade because the version is never signed. So the question is how to patch 1.3 to prevent downgrades. The finished messages don't help. So here is something ugly. Those that had a pure mind should have looked away. So we put the server version into the server nonce, and we do that for all past versions of TLS to obtain backward compatibility. So while this is a bit ugly, the good news is it works. And so we can prove downgrade security for servers and clients that support all versions, including TLS 1.3, as long as they implement this countermeasure and as long as they don't support RSA key transport, in which case there are just no signatures to help. So this is all I had to say for now.
So if I understand correctly, you still need to have one primitive that remains secure, in your case, a signature. So could you imagine something in which, for example, the security can be one of two primitives?
Yes, I think that it definitely could be the signature scheme and the PSK. And if your signature scheme were broken and you had a good PSK, you could still have security. So TLS 1.3 may even in certain modes have that property. Mm-hmm.